Hi, and welcome to the lecture 10 on machine learning. In this class, we will apply some of the optimization foundations to regression formulations. We begin with the gradient descent algorithm, which is basically an iterative algorithm that lets you find iterates one from the other based on a direction called the gradient direction. So recall that any iterative algorithm has the following form, which is wk plus 1 is wk plus some step size tk times the step direction. What we had noticed earlier is that the gradient points in the direction of maximum rate of increase of a function. What we do here is the obvious opposite, go in the direction of maximum rate of decrease, and that happens to coincide with the negative of the gradient. So the basic idea is to use negative of the gradient of the particular function f or e. You could just read all of these as a function e. So the gradient of e, negative of that. So for example, if we consider the ridge regression problem, we had found the gradient of the error function at wk to be phi 2 phi transpose phi wk plus 2 lambda I wk, that is basically 2 lambda wk minus phi transpose y. So the negative of that, if you add along with the step size, you get this expression in 8, 2 tk times phi transpose y minus phi transpose phi wk minus lambda wk. So the negative sign has just been used on each of these terms. So the general gradient descent idea is start with some initial point which is in the domain, move a small step. Now the one key step which actually depends on the specifics of the problem is the choice of the step size. So you could choose your step size either in an exact manner or in a backtracking manner. What does exact search mean? It means treat the problem of finding k as a one-dimensional optimization problem. Tk is basically that value of t that minimizes the objective function e or the error at the sum of the previous update plus t times the step direction. So you want to find that t that actually minimizes the error function along the fixed direction. So wk and delta wk are fixed in this optimization problem. It's a one-dimensional optimization problem. Often this is not very easy to solve. So backtracking ray search basically says I'm going to start with some value of t and then keep shrinking or modifying the step length till you meet some minimal descent condition. The other thing is how long will you keep doing these iterates. So the idea is, we expect the necessary condition to be satisfied, that is, we expect the gradient of E at the W star to be 0. That may not be possible, but what we can certainly look for is WK or WK plus 1, who gives a very small magnitude gradient of E evaluated at that point. So you want the gradient to be very small, the rate of change to be very small when you move around this point. So you would generally stop then. So the exact line search algorithm is basically a one-dimensional search problem, how far to move along a fixed direction starting from a fixed point. So this is the one-dimensional search problem for our specific ridge regression objective. So it's an interesting thing to note how quickly this can converge for ridge regression, because we already know that ridge regression has a closed form solution. So if you start with a W0 equals 0, you would expect T1 to give you convergence. So you would not need to iterate for too long. The gradient will actually vanish. And this is the spirit of gradient descent algorithm, moving from one level curve to the other. Of course, depending on the curvature, the rate of change and the direction of the rate of change, or maximum rate of change or minimum rate of change, can keep changing. In fact, the more elliptical the level curves are, the more the chances of oscillation, and so on. Now, how do you deal with the constraint form of the regression? In general, how do you incorporate constraints? How do you find that this is equivalent to the penalized form of ridge regression? Remember that we were interested in different values of p norms. So what do you do with these cases where p equals 1 or p equals infinity or p equals 0? P equals 2, at least we could solve the penalized version. Some of these others are not even easy to solve with the penalized version. So certainly you need some iterative method. In fact, what you use often is a variant of gradient descent called subgradient descent. More about that a little later. What the general constraint problem we're going to solve? We have be basically interested in convex functions. Recall that our convex functions look like this. The Hessian can be positive definite or even semi-definite. What is generally helpful is to assume convexity not only on F but also on the set. So a set is convex if any line segment connecting 2 points in that set also lies within that set completely. A very specific, I've said improved, but actually what I mean is a specific form of the constraint optimization problem is where the constraints are provided as a union of convex sets. So this is basically union of convex sets. How do you ensure that these are convex sets X such that what do I mean by convex set? I mean X such that GIX is less than equal to 0 is convex, and so on. So if Gi is itself convex, then certainly you can show that this set, each of this set is convex. In fact, this is called a sub-level set. Just like we talked about level curves or level set, in the sub-level set you replace the equality with an inequality. So you can show that if G is convex function, then sub-level set is convex. This doesn't necessarily hold the other way. It isn't that if the sub-level set is convex, G must be convex. And we can easily show counter examples. We also require the HIs to be affine. So any equality constraint HIX equal to 0 could be written as two inequality constraints, HIX less than or equal to 0 and minus HIX less than or equal to 0, which means both HIX and minus HIX being convex is desirable. Now both are convex would mean that HIX must be linear or affine. So affine is we will consider affine to be just linear functions. So how do you solve such a constraint optimization problem? Well, if the solution were the interior of the constraint, so this is the interior G1 x less than 0. If the solution x star were here, obviously we would expect that the function f isn't allowed to change around that point, or rather it's not allowed to increase or decrease around that point, which would mean that the gradient of f at x star, let's call this w star, would be 0. So this is the case of w star lying within the interior of the constraint set. The trickier question is, what about w star lying here, or w star lying at this point? And the answer is that you can visualize the function to be decomposed into two parts. F can be written as, or the gradient of f can be written as a component along the direction of G1 and a component perpendicular to the direction of G1. So what you will do is we'll consider f of f to be a linear combination of these two. So let's say theta and it's a linear combination, so you can just consider it to be theta and alpha. You don't want to be able to decrease the function f, move against the direction of gradient of f, while at the same time not changing or in fact decreasing the G1. Right, so key is no decrease in f should be possible while either decreasing G1 or letting G1 W to be equal to 0. That means moving, you should not be able to move in a direction that's perpendicular to G1, which means that the alpha, what we are talking about here as alpha, must be 0. But more about this in the next classes.